Okay, we are off to chapter 13 here, which is gases. Again, this chapter obviously has been moved from the exam, which is on Monday. So we're going to cover obviously through like we finished up last time. There's 9, I believe. So it should be 6, 7, and 9 coming up on Monday. So 13 here is about gases. We're obviously going to talk about gases and different gas laws that we will see here. We'll also talk about some gas stoichiometry in this equation or in this chapter as well. So let's get started with substances that sort of exist as gases under sort of normal conditions. So under normal conditions, you know, that's usually kind of table type conditions that you find for in books and so forth. And normally what that is sort of like a room temperature of 25 degrees Celsius and also a pressure of 1 atmosphere. 1 ATM is an atmosphere, obviously a unit of pressure. And that is typically what kind of normal sort of conditions are thought of as. And under those sort of normal conditions of 25 degrees Celsius and 1 atmosphere, ionic compounds typically are not found as gases under temperature. And that's really because ionic compounds are cations and anions, and those guys are held together by very strong electrostatic attraction. Opposites attract. And that is like pretty much your kind of super strong attraction that you could get. So under these conditions, you know, it really doesn't happen. Even if you apply a good amount of heat to it, you will not like transform something like sodium chloride into like the gas phase or anything like that. We saw this as well earlier on when we did some experiments where, you know, we had some salt water basically, and we evaporated off the water, and you're left with kind of just the salt that was left there in your evaporating dish. You could heat the heck out of that thing, and it pretty much will just melt. It will not go really into the gas phase because to overcome that really strong attractive force between that cation and anion in the solid phase, you know, it takes a lot of energy to do so, and it really doesn't happen. It will really start to melt before it actually even kind of tries to go into the gas phase. So covalent compounds, though, which are obviously our guys, are molecular compounds, which are our nonmetals and nonmetals together. They are very different than sort of ionic compounds. So a lot of molecular compounds, they actually are gases at room temperature and sort of room conditions. Things like carbon monoxide, carbon dioxide, that's hydrogen chloride gas, that's ammonia gas, CH4 is methane, which is your simplest organic guys, the stuff that comes out of the pipe there when we light a Bunsen burner, basically. Those guys pretty much will exist as gases under normal conditions. The major difference between sort of an ionic compound and a molecular compound is, unlike an ionic compound, molecular compounds are held together by kind of weaker intermolecular forces between the molecules. And what that means is much easier you can convert a molecular compound into a gas than you can an ionic compound. The pretty much simple example that we're all probably familiar with is good old H2O there. H2O is obviously normally found as a liquid, but not with a lot of effort, just some fire, right? Get it to about 100 degrees and you can convert it obviously very simply into sort of the gas phase. And that's because when water molecules are together, they're held together because water is polar, where oxygen is more negative, hydrogen is more positive. Because of that polarness, they're held together by what is referred to as hydrogen bonding. Hydrogen bonding is what is known as an intermolecular force. It is much weaker than an intramolecular force, which is like what holds an ionic compound together. Intramolecular forces are the ones that hold an individual sort of molecule together. Intermolecular forces are ones that hold two different molecules together, like two water molecules. So if we look at just the water molecule by itself, the covalent bonding that is happening here between the hydrogen and the oxygen on both sides, that is what is known as an intramolecular force within the molecule. That's the force that holds that together. The bond here between this entire water molecule and the other one is an intermolecular force. And intermolecular forces are always much weaker. And that's because when we start heating something like water, the first bond that breaks is actually the bond between the two different water molecules, and that allows each water molecule basically to escape into the gas phase. If it was opposite and the intramolecular force was weaker, when we would start heating, we would break these bonds, get hydrogen gas and oxygen gas being made, and that's probably not really great if you're heating it with a fire at that point. So because that intermolecular force, the force that holds the two water molecules together, is much, much weaker than the internal forces that hold individual water molecules together, it's much easier to kind of convert it into the gas phase. And that's basically what the general rule basically says. You know, the less the attractive force is, our strength of that attractive force between individual molecules, the much easier it would be to kind of convert it into a gas under normal conditions. Obviously, the much stronger two molecules are held together, it's going to take a lot more energy and much more difficult to kind of convert it into the gas phase. Any questions on that there? Now, we know some substances that normally exist as gases under normal conditions, and these are some of the ones we've talked about before. A lot of our diatomic molecules or elements here exist that way. So hydrogen, nitrogen, oxygen, fluorine, and chlorine, those are all elemental forms and how they normally come, and they normally do come as gases. Things like ozone here, which is good in certain cases in the environment and not so good in other parts. Also why we put sunblock on so we don't get too burnt. Is a gas, that's O3. We also have noble gases here, which is our group 8 on the periodic table, our neon, our argon, our krypton, all the ons there. And those are monoatomic gases. They come as ones basically, as opposed to obviously things like chlorine, nitrogen, and oxygen, which basically come as twos. So when we look at sort of the periodic table, you know, there's sort of a section of things that under normal conditions basically do come as gases, and that's pretty much our hydrogen. Then obviously everybody kind of on this side here comes naturally as gases. So when we talk about gases, there really is a difference between two words that are sometimes sort of used interchangeable, and that is a gas and a vapor. A gas is a substance that normally would be found in the gas phase under normal conditions. A vapor is something that is normally not found in the gas phase, but has been converted into a gas. And that is why, if you think back to sort of the gas experiments we did the other week, we talked about getting the water vapor pressure, right? And that's because when we talk about water in sort of the gas phase, we call it steam or water vapor. And that's again because water is normally found in the liquid state and obviously is converted into the gas phase. When we talk about gases, obviously we were talking about the state of matter where pretty much everybody has broken apart from one another and they are flying around in a container. And as they are flying around the container, there are collisions that occur. And it is these collisions that basically cause the pressure that we associate with gases. So the more collisions that occur between the gas and sort of the container, the higher the pressure that we would assume that would occur, and vice versa. The less sort of collisions that we have that are occurring there between the gas and sort of the container, the lower the pressure that we would assume to have. So pressure obviously is a very big measurable property that we talk about with gases. By the way, air is mainly nitrogen and oxygen is second in terms of the actual gases that you have there, plus some argon, carbon dioxide, and I guess wherever you're sitting at that point, whatever else is floating in the air. But the majority of it is nitrogen, is made up of air. One of the measurable properties of a gas, like I said, is its pressure, and it is related to the collisions that occur between the, really in most cases, the gas molecule and the sides of the container. So as they're moving around and banging into that container, causing those collisions that occur. Now, one way that we really do measure pressure is with a barometer, and a barometer is an instrument that measures pressure. Old-time barometers used to be a pool of mercury with basically a tube that's in there. And basically what would happen is, as again, atmospheric pressure sort of went down on the mercury that was in the barometer, the mercury in the tube would start to rise, and you would take a mercury reading. Mercury actually has an inverse meniscus. It actually goes upward in terms of that. So when you would read it, you actually would read the top of the meniscus. And in this particular case, one of the most common ways that we would read it is there would be a ruler there on the side, and you could read it in inches of mercury, which is millimeters of mercury, or centimeters of mercury, and you would take your barometer reading. Obviously, as we use in class there the other last week, you have digital barometers that you could use. We also have one over the sink there by the oven. Is a barometer, more of an alcohol sort of barometer. There's a thermometer and a barometer that's hanging on the sink or above the sink there in lab. So those mercury ones have been removed from a lot of places because they contain mercury, but that's a very common way the barometer used to be. And that gives us our sort of common units that we see with pressure. An ATM, which is an atmosphere, is the probably most common unit of pressure that we deal with. A torr, which is named after the guy who invented the barometer, is equal to 1 millimeter of mercury. And again, that's basically because you would take that reading when you read the barometer. And they are equal to each other in the sense it's a one-to-one relationship between a torr and a millimeter mercury. So if you have to do that conversion, you just simply change the units, the number stays the same. And this is our relationship between those three units. An atmosphere is equal to 760 millimeters of mercury, or 760 torr. So as we probably talked about the other day, if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by that 760, and that will give you millimeters of mercury or torr, which again is a one-to-one relationship. Or vice versa, if you have millimeters of mercury or torr and you want atmospheres, you're going to divide by the 760. We'll get you there in this particular case. There obviously are other units of pressure that we come across, like PSI, right? Pounds per square inch. A Pascal or a kilopascal is another kind of unit of pressure. A bar is another common unit of pressure that you sometimes come across. A bar and an atmosphere pretty much almost equal to each other. It's like 1.01 equals 1 atmosphere. They're very close to each other. So I would say probably though in most chemistry classes, these are the big three units that you do come across, but obviously there are different units that you could come across here. Any questions on that there? All right. And again, here's some of those other units, pascals, pounds per square inch, 1 atmosphere. So 1 atmosphere is 14.7 PSI, and there are 760 conversions there. Are inches of mercury, which is a common way you would read off a barometer, and that is our kilopascals there as a unit. There's a much prettier picture than the barometer I drew, but same idea here. Again, atmospheric pressure, mercury rising, saying that you hear sometimes, right, is again the mercury rising there in the tube, and you basically take a reading. The SI unit of pressure is a Pascal, and again, here's the relationship. Not too much of use of Pascals, really, too much in general chemistry and stuff like that. So, but in case you want it, 101,000 Pascals or 101.3 kilopascals. And again, we probably won't use Pascals in here very much at all, if anything. All right, so let us talk about some gas laws here. And when we talk about gas laws, there's really sort of three variables that we deal with. We deal with basically when we talk about gases, pressure, volume, and temperature. So these are the three sort of big things that we deal with when we talk about gas laws. And a lot of gas laws, we oftentimes will keep one of these things constant and sort of vary the others. Sometimes we'll kind of use all three of them together, but these are the big three that we sort of look at. So the first one is Boyles Law, and Boyle studied the relationship between pressure and volume. And he looked at pressure and volume, and he held temperature constant in his experiments. And what he found was that a fixed amount of gas at constant temperature is inversely proportional to the gas pressure. So that's what it is. Pressure is proportional to 1 over the volume. It gives us this relationship that the volume is equal to K1 times 1 over P, which is PV equals K1. This is what is sometimes referred to as a proportionality constant. And basically what that means is if you did sort of like a Boyles Law experiment and you held the temperature constant, if you look at measurements for a gas and you always took the pressure with the related volume at that point and you multiply it together, you'll always get a constant number is basically what that means. So you always end up with a constant number if you're sort of following pressure and volume changes with the gas at constant temperature. And what that means is if you end up with a constant number, it allows us really to sort of get to really what is Boyles Law, which is you can kind of do a before and after situation, because every time you do a pressure volume, they are equal to each other. And that allows us to get to really what Boyles Law is right there, which is P1 times V1 is equal to P2 times V2. This is at constant temperature. The P's here are pressure. They could be any unit you like as long as they are the same on both sides, so all the units cancel. The V, which is volumes here, same deal, can be any unit you like in terms of volume as long as they're the same on both sides, so everything cancels out completely. This is sort of like a before and after situation here. Kind of, you change maybe the pressure, you change the volume, and you can see how the other one basically reacts to it. There is an important relationship between pressure and volume, and it is this: as the pressure goes up, the volume goes down, is basically what they saw, and vice versa. As the pressure goes down, the volume will go up. So that is basically Boyles Law relationship there. That's the inverse relationship. And if you just think about it, if you have a very small volume with all your gas molecules in there, there is going to be a very good chance of a lot of collisions happening, right? Because there's not a lot of room for everybody to fly around in. More collisions, more pressure. As opposed to if you kind of gave everybody a lot more room to fly around in, right? It's going to take longer for collisions to occur. Less collisions are probably going to happen. Everybody's got a little bit more room to kind of fly around in, and you would start to see the pressure come down in that particular case. So you would have kind of less collisions here, and you would see your pressure basically come down. So basically opposite relationships in Boyles Law. The relationship here is a good thing to keep in mind when you do some calculations to make sure you didn't screw up on your calculation. Everything sort of makes sense when you get there. Any questions on that? Yeah. Yeah. It's a proportional symbol. This guy right here, I think. It's supposed to be a proportional symbol. Yeah. And it's basically just saying this right here, that it's the opposite relationship. Yeah. This one goes up, the other one goes down. Yeah. Other questions on that? And that's what we see from a graph here for a particular gas. If we look at the volume here, at much smaller volumes, we have a much higher pressure. As the volume increases as we go this way, it gives everybody a lot more room. Less collisions start to occur, and we do see a significant decrease in the pressure that happens. And that really is sort of our Boyles Law relationship. So why don't we try one here? An inflated balloon has a volume of 0.55 liters at sea level and rises to 6.5 kilometers where the pressure is 0.4. Assuming the temperature remains constant, what is the final volume of the balloon? So take a minute or two, see what you come up with. Let's take a look at this. And when you're dealing with gas sort of problems and gas laws, it's a good idea to sort of pull out the information from the problem and kind of label what everything is. And really what you'll be able to do is obviously probably help you pick the right gas law. Obviously, we're going to do Boyles Law here since it's the only one we've talked about so far, but we have 0.55 liters, which is a volume. At sea level, which is 1 atmosphere, that is a pressure. It rises to 6.5 kilometers, which is useless information. And it goes to a pressure that is 0.4 atmospheres. And we are looking for a volume here. So again, if you weren't sure, you could kind of see Boyles Law right there by just kind of labeling everything. And obviously we would be using P1, V1 equals P2, V2. In terms of units, we do need to check our pressures since we have 2 of them and they're both in atmospheres, which means we're good to go. Obviously, if one was atmospheres, one was inches, millimeters of mercury, you got to do a conversion to either one. It doesn't really matter. Doesn't matter which ones you call 1 and 2. It doesn't, as long as you keep the numbers that go together. So it doesn't really matter which ones you call. So in this case here, we would have our 1 atmosphere times our 0.55 liters equals our 0.4 atmospheres and our V2. Obviously, we're solving for V2, so we're going to take P2 to the other side, right? So that they cancel. In gas laws, when you move across the equal sign, everybody ends up in the opposite location, right? So really P2 is up on top on the right, ends up on the bottom left as you go across the equal sign. That's a quick way of rearranging equations. You have an equal sign. Basically, everybody ends up in the opposite location if you need to move them across the equal sign. So we will be obviously dividing the 0.4 to the other side there. It gives us 1 atmosphere, 0.55 liters equals V2 divided by 0.4 atmospheres. The atmospheres here will cancel. That's going to leave us units of liters, which is good since we are looking for a volume here. So 0.55 basically divided by 0.4 gives us a V2 of 1.4 liters in this case. Any questions on that? Now, this is a case where, you know, if you understand the relationship of Boyles Law, what we see here when we look at the pressure is, in this case, the pressure went down, which means we should know the volume should go up. And it started at 0.55, ended at 1.4. So that makes sense based on what we know in terms of what's happening here with Boyles Law. So that's a good idea to kind of understand those relationships. Can help you make sure your answer sort of makes sense. Any questions on any of that there? Yeah. I'm sorry, how did I do? How did I solve for V2? Is that what you're asking? Yeah, so we had P1, V1 equals P2, V2. In this case, we pretty much had that guy, and that guy. So we wanted to solve for this guy. And typically, whatever you're solving for needs to be by itself on top, if you will. So that means we kind of have to get rid of this guy, right? So we got to divide him to the other side. And he ends up over there. And again, if you want to do sort of the just arrow type of deal, we need to move this guy to the other side, which means he ends up on the bottom. You know, that's pretty much what will happen. Other questions on that? Okay. All right. So the next couple of laws we're going to talk about is Charles' Law and Gay-Lussac's law. And Charles' Law really dealt with the relationship between volume and temperature, and he held pressure constant. Gay-Lussac's law really dealt with pressure and temperature, and he held volume constant. So those are sort of the two gas laws that are very similar to each other, except obviously one is dealing with volume and temperature, and the other one is obviously dealing with sort of pressure and temperature. And when we think about what would happen in sort of each of these situations, what happens with Charles' law and the volume and the temperature and the constant pressure, and sort of Gay-Lussac's where we deal with pressure and temperature and the volume is constant. I'll spit that out, I think. Let's start with the constant volume. If I had a constant volume and my volume, my container is not going to change, and I have gas molecules in there, if I increase the temperature, will my gas molecules be moving faster or slower? They should be moving faster, right? The old saying, light a match under you, you start moving, right? So same idea. If you increase the temperature, gas molecules should be flying around faster, which means there should be more collisions occurring, right? Because they're flying around a lot faster. And in this particular case, my volume is constant, which means it's not going to go anywhere. So we're going to have gas molecules flying around faster. We're going to have more collisions when we increase the temperature. That all should result in an increase in pressure because of that. And vice versa in this situation, if we decrease the temperature, gas molecules are going to start to fly around a lot slower. It's going to cause less collisions to occur. And basically, we would actually see the pressure start to go down in sort of this situation here. Any questions on that there? So what happens in sort of Charles' law, where we have constant pressure, that means that we cannot have the pressure go up or down. So something has to happen, keep it at constant pressure. So if we take our same sort of box here with our gas molecule and we heat it up, a fine looking Bunsen burner right there. If we start heating up, we're going to have the same situations that's going to occur as below. We're going to have our gas molecules starting to fly around a lot faster, going to cause more collisions. So what happens in Charles' law situation is the volume actually expands. So what ends up happening is, even though they are flying around a lot faster, they have a lot more room to fly around in. And what that ends up doing is keeping the number of collisions relatively constant. And that obviously would then keep the pressure relatively constant. So what we see in Charles' law is, as the temperature increases, the volume will also increase to maintain the pressure and keep it at constant pressure, and vice versa. If we lowered the temperature, we would have our less collisions. So when we lower the temperature, what happens is the volume actually comes down to keep the level of collisions occurring. So it kind of squishes everybody together, keeps the collisions occurring at the same rate, and we actually see that the volume will decrease with it. So in the bottom case, the volume is stuck in place, it's rigid. So as we increase that temperature, we do see the pressure kind of change, either go up with increased temperature or go down with decreased temperature. But in the situation where we want to keep it at constant pressure, we do have the volume basically adjusting to maintain the constant pressure. Any questions on that there? Now, there's an important relationship when we look at a graph of what happens here. Let me see, I think the graph is next. We'll look at it first, and we'll go back to that page. If we graph volume versus temperature in sort of a Charles' law situation, and you do it for any gas that you like, and you basically extend those lines back to the temperature scale, every single gas ends up at the exact same number, which is minus 273.15 degrees Celsius. That number looks familiar. That is the number that we use basically to do what? 273 is the number we use to convert to Kelvin. So Kelvin was a guy that sort of recognized this. He called this absolute zero, because if I convert this to Kelvin, I'm going to add 273.15 and gives me 0 Kelvin, which is absolute zero. Yes. So Kelvin recognized this fact, and because of that, you could thank him, because pretty much every single gas law that you ever come across, if you have temperature, it needs to be in Kelvin. So you got to always make sure that the temperature in gas laws are in Kelvin 100% of the time. I don't personally know of any gas law that does not use Kelvin for the temperature. Even in questions where they may try to trick you in books, they will give you the temperature in Celsius. They will ask you to give the answer in Celsius. So people think, well, they gave it to me in Celsius, I need to give the answer in Celsius. I could just put it into the gas law in Celsius. You cannot do that. You will get the wrong answer. So you have to go convert it to Kelvin, put it into the gas law, and then convert it from Kelvin back to Celsius for the answer. So 100% of the time, because of this relationship, what we see is that the temperature always has to be in Kelvin. And again, that is basically a reminder, like we see there, Kelvin is 273 plus our temperature in Celsius there will allow you to do that. Any questions on that there? So Charles' law and Gay-Lussac's law and some other laws that we see that involve temperature, again, always needs to be in Kelvin. That's a very common mistake people make. They leave it in Celsius. So make sure you don't do that for sure. Like normally you could kill the 0.15 part of that number and just use obviously 273. You're okay, like normal. So let's take a look at really what those laws are for each of these guys. And we do get the same sort of proportionality constant that we saw with Boyles' law. If you take the volume divided by the temperature for any situation with the same gas, it will always equal the same number. That allows us really to put it together. And this is really sort of Charles' law here. And that is V1 over T1 is equal to V2 over T2. And the main importance is obviously, as we just talked about, and as it says there, temperature does need to be in Kelvin. And that's obviously on both sides. It needs to be in Kelvin. Now, Gay-Lussac's law is P1 over T1 is equal to P2 over T2. And this is at constant volume. This is obviously at constant pressure. And these are the relationships that we talked about. Again, as the pressure goes up, so does the temperature. And as the pressure goes down, so does the temperature for that guy. And down here, volume goes up, so does the temperature. And volume goes down, so does the temperature as well. So those are the important relationships for both of those guys. And obviously up here for Gay-Lussac's as well does need to be in Kelvin. Now, in terms of the pressures for the top equation there are the volume for the bottom equation. Again, doesn't matter. It could be any unit of pressure or any unit of volume. Again, as long as they are the same on both sides, so all the units cancel. So that's the important part there. Any questions on any of that there? All right, so let's take a look at one here and try, I think. In an experiment, 452 milliliters of a gas is used in a light bulb. It's heated from 22 degrees Celsius to 187 degrees Celsius. What is the final volume? So take a couple minutes, see what you come up with. Okay, let's take a look. So now we got a few gas laws to choose from. We got our Boyles. We got our Charles. Our guy that's very similar there, P1 over T1 is equal to P2 over T2. So again, if you're not sure which one to use, we pull out the information. We obviously have a volume that is 452 milliliters. It is heated from 22 degrees Celsius to 187, and we are looking for a volume. So again, just kind of pulling out the information. Clearly, none of these would work since there's no pressures involved. So we can kind of even kind of see almost Charles' law there. As was a question that was asked earlier, even though they're both in the same units of temperature here, you got to go into Kelvin to get the correct answer regardless of that. So here we do want to make sure that we do convert our temperature to Kelvin. We're going to do a 273 addition on each of these guys. And that will get us a 273 plus a 22, gives us a 295 Kelvin, and a 187 plus a 273 gets us a 460 Kelvin. At this point, we are good. We could call the first set of guys ones if you like, and the second one twos. That means when we look at V1 over T1 is equal to V2 over T2, we're actually looking to solve for V2. So again, quick way is that's just going to go to the opposite location, and that will give you V1 T2 divided by T1 is equal to V2. We're basically multiplying T2 to both sides. Is essentially what we're doing there. At this point, we want to make sure that we actually put the correct numbers in the correct locations. Also a very common error. People put T1 in the T2 spot and so forth. So here we are looking for our V1, which is 452. Our T2, which would be the 460 Kelvin, divided by our T1, which would be the 295 Kelvin, and that would equal our V2. Here, the Kelvin and the Kelvin will cancel. Will leave us units of milliliters, which is good since it's a volume. That is going to get us a 460 times 452 divided by a 295 over there. We'll call it like a 705 milliliters would be our answer here. First off, any questions on the calculation part? Again, understanding the relationship that is here when we see Charles' law and we look at what's happening with our temperature is going up, which means we would expect our volume to follow and also go up. We started at 452, it went up to 705. So again, it makes sense based on the relationship that we should be seeing here with Charles' law. And that's also, again, like I said, a very good way to check yourself, because very common people kind of invert numbers a lot of times when they're doing these calculations. Any questions on that there? All right, well, our good friend Avogadro, he had a number, but I think he wanted a gas law as well. So I think that was his dream. So Avogadro does have a gas law. I know, I talked to him. It was his dream, it was. So when we think about avocado, what's that avocado? When we think about avocado, we think about moles, right? 1 mole is equal to 6.022 times 10 to the 23. So why would his gas law not involve moles? And it actually does. This is actually at constant temperature and pressure. So under constant temperature and pressure conditions, we get Avogadro's law here, which is V1 over N1 is equal to V2 over N2. N is the moles, basically. So N is moles, obviously moles of gases here. There's sort of an interesting relationship with Avogadro's law, which is basically as the moles increase, so does the volume sort of increase proportionally to it. And as we will see a little bit later on this chapter, it will allow us to sort of bypass some parts of the calculation when we're doing stoichiometry that happens under constant temperature and pressure. What we can do is if we look at an equation that's all gases, and from an equation, right, we normally could do our stoichiometry relationships and go, hey, there are 2 moles of A gets us 1 mole of B. We could do, right, 2 moles of A gets us 3 moles of C, and so forth. If this was occurring at constant temperature and pressure, we could actually come up with a relationship that actually involves volumes. So a lot of times when we're dealing with gases, we're interested in how much volume of gas you collected, kind of like your experiments, right? You're interested in how much of the volume of the gas you actually collected. So we actually can, if we have sort of a gas stoichiometry relationship here, use sort of Avogadro's relationship to go, that is like 2 liters of A is equal to 2 liters of 1 liter of B. We could say that for 2 liters of A, we get 3 liters of C. So instead of like a mole to mole relationship, we could kind of do a volume to volume relationship as long as it's under constant pressure and temperature. And it will allow you really to bypass using the gas law to figure out how much volume you would collect and so forth. And we'll see this a little bit later on in some examples here in this chapter. So that's sort of one consequence of Avogadro's law, is sort of this relationship of moles and volume sort of being equal to each other in a sense when we're under those constant pressure and temperature conditions. Obviously, the volume here in the calculation on the bottom can be any volume unit you want, and clearly the moles need to be in moles to use that. And that's what we see here. Again, as I was just mentioning, we could do sort of a volume to volume relationship, and is equivalent to like the mole to mole relationship. So again, we could say 1 liter of H2 gives us 1 liter of Cl2, or 2 liters of HCl. And again, we could almost do a stoichiometry relationship under these constant pressure and temperature relationships. Now, putting together all those wonderful gas laws that we talked about are Boyles, Charles, Avogadro's law. We got the granddaddy of them all, which is the ideal gas law. And it is obviously a gas law that works for ideal gases. You may be saying to yourself, what is an ideal gas? Well, it's pretty much every gas we deal with. We assume sort of ideal conditions. And we'll talk a little bit about what that is later on in this chapter. Pretty much all gases that we deal with in this class will be ideal gases. If you take Chem 1A, you will talk about real gases, unlike these fake gases. You'll talk about real gases, which do behave a little bit differently. We really only get into sort of what is sometimes called real gases when you get really high pressures and really low temperatures. So you get that sort of big extremes. But under normal conditions, most gases will behave ideally. And ideal gas law is PV equals nRT. It is different than all the gas laws we've seen up to this point. There is like a no before and after type of situation. It is a one and done situation here. One pressure, one volume, one temperature, 1 mole. And it is also the most restrictive in terms of units. If you are using the ideal gas law, the pressure has to be in units of atmosphere. The volume has to be in units of liters. Moles should be moles, or something is really wrong. And temperature, like everything else, does need to be in Kelvin, if I can spell that, Kelvin. And the reason why pretty much everybody needs to be in those specific units is because of R. R is the gas constant, and it is a value that you always have available to you. Although in a lot of problems, they will not tell you, hey, R is this. They just assume that you know what R is. So you always got to keep in your head that you do have that sort of available to you. R is 0.08206. The units are liters times atmosphere divided by Kelvin times mole. And that is why everybody else needs to be in those units so that everything properly cancels out. People will nowadays round this number and use it as 0.0821. You could use either number is fine. I use this number because that's what they beat in my head and I can't get it out as much as I try. So, but a lot of books and stuff will now use more of the rounded number, the 0.0821. And again, either one's fine. The good news is somewhere on the paper, you probably have this number given to you with the units, which is a nice reminder in case you forget what the units of this guy should be. You can just look at the units of R and it will tell you pretty much, obviously, what everybody else needs to be in for it to properly cancel out. Any questions on that there? Yeah. Yes, it will definitely be on the paper somewhere. Unless I forget, then it won't be on the paper, but I'll try not to forget. But yeah, it's usually on there. But again, in problems and stuff like book problems, stuff like that, it's usually not mentioned at all. So, you just got to remember that you always sort of have that number and you could look it up obviously in the book if you needed to. Other questions on that? Okay. Now, there's a couple of other sort of important relationships and gases that we're going to talk about here and sort of how we use them. The first one is, we'll start with STP. STP, as we talked about, I think in lab, stands for standard temperature and pressure. And when it does say under STP conditions, what it means is they are actually giving you a temperature, and that temperature, as it says there, is 273 Kelvin, and that pressure is really 1 atmosphere. So again, sometimes in a problem, they'll just say add STP conditions or something, or add STP. And you're like, well, where's all my numbers? And again, it is actually giving you 2 numbers that you could use. You could stick it into the ideal gas law, obviously using the temperature at 273 and the pressure at 1 atmosphere. Now, there is a really nice relationship that occurs when you are at STP, and only at STP is what this is over here. 1 mole of any gas will equal 22.414 liters. So this conversion factor here can only be used if you're at STP, which means you got to have that temperature at 273. It has to be 1 atmosphere for the pressure. If it is not at STP, you should never ever use that little conversion there. Yeah. The good news is you can use the ideal gas law at STP conditions, non-STP conditions. You could use it for any conditions, the ideal gas law. So if you're unsure if you should use that in a particular situation, don't use it. Just go use the ideal gas law and you'll be fine. The benefit of that conversion is if you happen to be at STP conditions, you could bypass the ideal gas law and just do like a conversion. And that will a lot of times allow you not to have to use it. And you can kind of quickly calculate something that you're looking for. So it's sort of a quick conversion at STP conditions that allows you not to have to use the ideal gas law, but you absolutely could use the ideal gas law in any condition that you need. Any question on that there? This is also really how we get to the gas constant. If we take the ideal gas law, which is what this is, and solve for R, and put in all the conditions under STP, that would be 1 atmosphere, that would be 22.4 liters, that would be 1 mole, and 273. That's essentially where the gas constant actually comes from. This R value, that 0.08206, is the gas constant that we use for gas laws. Later on, there is a few different versions of R, like 8.314 joules per Kelvin per mole. That is one that we use for energy type calculations that we don't use in this class, but you will use in 1A and stuff like that. So there are some different versions of R. So if you look around and you like search R, you will see some different values. But the one that you definitely should use for gas law purposes is this one here, the 0.08206 number. Don't use any of the other ones. Otherwise, your units are going to be way, way wrong and you're going to be off on your number. All right, well, all that build up, let's do one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a vessel that has a volume of 5.4 liters and a temperature of 69.5. Not sure what to use in terms of gas laws. We are obviously looking for a pressure. We have moles given to us. We also have a volume. And we have a temperature, which is 69.5 degrees Celsius. So just kind of peeking at that, that should kind of really point you to the ideal gas law. Clearly, we don't have 2 of anything else, so we can't use any of the other ones. So we definitely will be using our PV equals nRT here. In this particular case, we are solving for P. So we basically need to bring the V to the other side. And that will give us P is equal to nRT divided by V. We want to look at some of our units here. So moles is good. Our volume is in liters, so that is good. And much like a problem here, our Celsius there does need to be converted. So we're going to do 69.5 plus a 273. So here we will add 273, and that will get us a 342.5 Kelvin. Remember that although not mentioned in the problem, like usual, we always have R available to us, which is also a missing piece. So at this point, we now have everybody in the correct units. So putting it in would give us 1.82 moles. Are 0.08206 liters atmosphere Kelvin mole. Our temperature of 342.5 Kelvin divided by our volume of 5.43 liters. The moles here will cancel, the Kelvin will cancel, the liters will cancel. That is going to leave just atmospheres left in terms of the unit, which is good because we're looking for a pressure. 1.82 times 0.08206 times a 342.5 divided by a 5.43 gets us a pressure here of 9.42 atmospheres, which is a pretty big pressure there. First off, any questions on the calculation? Now, a couple of variations of this. Volumes are oftentimes given in milliliters, kind of like how you collected your gas, right? So doing the milliliters to liters conversion is a very common thing that you need to do. Also, a lot of times you're given things in grams. So converting grams to moles using the molar mass is also another common sort of step here that you sometimes have to do, obviously, before you get it into the ideal gas law. Any questions on that there? Yes. R is just a constant, so you always have it. So it's always that number. It's always sort of available to you. Yeah. And again, like I said, a lot of times they just don't tell you anything about R in the problem. So they just assume you know you have that available to you. Other questions? Okay. So there is a gas law that really deals with all three variables together. And it's actually the one that we kind of talked about in that lab we did, I think, with the hydrogen gas. And it really is derived from taking really the ideal gas law and solving for R in each case, R, which is obviously the gas constant, right? So these two numbers are the same, which means you could put both of these guys together. And in most cases, what happens is if you don't open the lid, the gas is not going to escape, which means the moles of gas that you have in there will be the same. So what this gets us is to this equation here, which is sometimes referred to as the combined gas law, because it pretty much combines all the variables together here. And it is P1 V1 over T1 is equal to P2 V2 over T2. The pressure here on both sides could be any unit, again, as long as they are the same. The volume here can be any unit, as long as they are the same. And like normal, our temperature does need to be in Kelvin. This is the one I would say gives most people a very difficult time rearranging. So again, just going opposite locations is a good way to kind of rearrange what you need. This is also a really good one to remember when you are maybe trying to think about having to remember all the other gas laws, because essentially if you remember this one and you understand what is happening in the other gas laws. So for example, if you are at constant, oops, helps if you have something to write with, I suppose that would be good. If you're at constant temperature, all you have to do is like do a scratcheroo there, and that is Boyles Law right there. Now, if you are at constant volume, for example, you take out your volume, and there's your P1 T1 is equal to P2 T2. If you're at constant pressure, you take out the pressure and you're left with V1 T1 equals V2 T2. So from sort of combined gas law, you pretty much take out the thing that's constant or it's not changing, and you could have pretty much all the other ones that we talked about. So it's a good one to remember, and just you get to all the other ones really quickly that way if you don't want to remember them sort of individually. Any questions on that there? All right, so let's try our math skills here. Let's see how we do. All right, so a sample of oxygen gas, 27 degrees, and a volume of 9.55 liters, and a pressure of 2.97. We change the pressure to 8.25 atmospheres and heat it up to 125. What is the new volume here? Okay, let's take a look since we're getting to the end here. Consider the temperature here. So we have a temperature of 27 degrees Celsius. We have a volume that goes with that of 9.55 liters, and we have a pressure of 2.97 atmospheres. We then change the pressure there to 8.25. We also have a temperature of 125 degrees Celsius, and we are looking for a volume. So again, by just sort of putting everything labeled, that should hopefully point you in the direction of the combined gas law, which is really kind of the only one that has all those guys together. That means we got a P1 V1 over T1 equal to P2 V2 over T2. In this case, we are looking for V2. So again, if you want to kind of do the quick conversion there, that means we got to take V2 to the top and bring P2 to the bottom, basically. That will give us P1 V1 T2 divided by T1, and P2 will equal our volume. We're basically multiplying T2 to both sides and dividing by P2 to the other side. Yeah. Any questions on that rearranging? All right, we want to check units here. So we got atmospheres on both sides. It's good. Our temperature obviously does need to be converted. So that is going to be a 2727 plus a 273. That's going to be a 300 Kelvin for this guy. And it's going to be a 125 plus a 273. That's going to be a 398 Kelvin in this case. That is everybody we need. So we want to put everybody in the right spot. So we're going to start with P1, which is 2.97. Our V1, which is 9.55 liters. And again, here we actually want T2 up on top, which is 398 Kelvin, divided by our T1 on the bottom, which is 300 Kelvin, and our P2, which is 8.25 atmospheres. The Kelvin up on top and bottom will cancel. The atmospheres up on top and bottom will cancel. That's going to leave us obviously only liters up on top, which is okay because that is a volume. So multiplying everything on the top, coming back and dividing by what's on the bottom there gets us, looks like a 4.56 liters again would be the unit, as that is the only unit that is left here. Any questions on any of those things? If rearranging equations are difficult for you, you should take some time to make sure you properly know how to rearrange them, because obviously you need to be able to solve for any of the variables that are in any of those sort of equations. Any questions on any of that?